Good afternoon. On behalf of IASTA, I welcome all who have joined us for attending 20th lecture of IASTA monthly online lecture series. I am Manish Joshi, Secretary, Indian Aerosol Science and Technology Association. Many of you know that this organization was formed way back in 1988, and afterwards it continuously promotes exchange of knowledge, mainly pertaining to aerosol science and its applications. We have a huge group as on today. This lecture series was started in 2023, 20th lecture in the series and third lecture for this year. And I'm happy to note that we are having a very distinguished speaker for today's lecture. Before we move to the lecture, I would like to just update all who have joined this for this lecture about the developments which are happening for Asian Aerosol Conference. Many of you must be knowing that India or IASTA is hosting 14th Asian Aerosol Conference between 1st to 4th December 2025 in Mumbai, India. So you can visit our website, which is www.aacindia2025.in, to get the feeds which will be regularly posted on our website. The important announcement is now our online abstract submission is live and the deadline is 15th August. However, I will urge you to submit your papers as soon as possible because our review process will be dynamic. We will be reviewing the papers continuously as we are getting the papers, and we will be posting the decisions as soon as possible from our end as well. There will be a lot of other activities around this conference, and I am hopeful that all of you will be coming to Mumbai to join us for a very interesting and very successful conference which we plan to have. So with this now, maybe we will be coming back to today's lecture. So to tell more about the lecture and the distinguished speaker, I'm inviting my colleague, Dr. Sunny Tiwari, and he can now take you forward.
Manish, I will be doing that. Manish, okay. Okay, good afternoon, everyone. I am Neeraj Rastogi, and it is indeed my pleasure to introduce today's speaker, who happens to be my friend since last 25 years. So, today's speaker is Dr. Pawan Gupta. He's a scientist in Biospheric Sciences Laboratory at NASA's Goddard Space Flight Center at Greenbelt, Maryland in USA. I know him since, as I said, since last 25 years when he was doing project here at PRL with Professor Jaraman. After that, he went for PhD and he completed PhD in atmospheric science from University of Alabama in Huntsville, USA. His main research expertise is in the application of satellite remote sensing for air quality monitoring and assessment around the world. He also works on air quality in growing megacities, spatial and temporal trends in aerosols, predatory effects of aerosols, development of a statistical model to estimate surface level particulate matter air quality, aerosol and cloud data validation, and retrieval of cloud products from satellite measurement, etc. He has published numerous papers in many high-impact reputed journals. He managed more than 20 research projects spread out across multiple applied sciences research areas and which are operational in more than 30 countries. So his spatial domain is quite big, as we can see. He co-leads NASA's Aeronet program. He is a member of NASA's multiple mission and science teams, including MODIS, WEIRS, NASA Citizen Science, Majors is making Earth system data record for use in research environments. And also HACAST. HACAST is Health and Air Quality Applied Science team. With these few words, I invite Dr. Gupta to deliver this talk. Dr. Gupta, please take it.
Thank you. Thank you, Neeraj and Manish. I really appreciate for this opportunity, and I'm really happy to be here. So let me share my screen and see if it works again. Okay, Neeraj, is this working fine?
Yes.
Okay, great. Thank you. Thank you, everyone. Thank you for attending. So today I'm going to talk about air quality monitoring and forecasting, and going to touch base on different aspects, ground measurements, satellite, and models. In this talk actually focused a lot more on some of the data sets which we developed, as Neeraj introduced here at NASA Goddard. I'm involved much more on measurements with Aeronet, satellite retrieval, generating or developing new data sets, and also more recently doing some machine learning, deep learning, including with the geophysical models. So it's a hybrid approach to assess the atmospheric aerosol or air quality from different perspective. But the major part of my job is to generate uh, measurements or data sets which can be used for the global reasons. As we work with the satellite data, the coverage is global, so we try to focus on global regions. So a lot of my presentation will focus on showing some new data sets which we have been generating. And then I will also demonstrate some case studies, some of the uh, project which actually went from research to operation and has been used by many different agencies around the world in their operational day-to-day work. So with that, let me start with this slide. This is just everyone knows that when it comes to air pollution management, in other words, the monitoring and forecasting, then traditionally we rely on ground measurements. And the ground measurements are typically point measurement. They have a small spatial coverage, but they are also most accurate in terms of what is happening near the ground, what is happening at the nose level air pollution which we breathe. So those are very, very critical component of air quality, air pollution management, having those ground measurement, whether they are for optical measurements or sampler for chemical composition analysis or mass concentration. It doesn't matter. They provides one of the most accurate assessment of actual condition at the ground. In last 2-3 decades, we have really advanced satellite remote sensing, looking these atmospheric component pollutant from space. And as you see on this left side, there have been fleet of Earth observing satellites from NASA, from JAXA, from European Space Agency, from India, from China, and all other countries. And there are so many now that a lot of them actually focused on making atmospheric composition measurement. And we'll get into some of the example of those. So satellite observation has become an essential tool in air pollution monitoring and assimilating into forecasting model, and they are complementary to the ground measurement. Remember, they are not going to replace the ground measurement, but they are complementary information. They can fill the spatial gap. They can provide some more measurements in areas where we don't have any ground measurements. So they are complementary. Yes, they are less accurate than the ground measurement, but they have very specific roles to play. And then comes to the model. If you want to forecast what is going to happen, just like weather, what will be the temperature in the night, tomorrow morning, or day after tomorrow, we rely on the model. So for air quality forecasting, around the world, different people have different models. There are global models which provides like NASA's GEOS, which we'll talk a little bit later. And then there are other models like ECMWF and CAMS, GFDL has, Navy has, other people have. And then a lot of regional models like WRF-CAM, CMAC, and other kind of regional model where people are trying to forecast local, regional, and global scale air pollution or air pollutant. So these three components together actually makes a hybrid approach for air quality or air pollution, in other words, management, which include monitoring and forecasting. So since I'm going to talk a lot about a couple of things, so I want to clarify the two terminology which you will hear often in my talk. One is aerosol optical depth, and another one is PM2.5. I'm sure all of you are aware of those two. Just want to refresh everyone's memory. That PM2.5 is mass concentration, which we make measured at near the surface. So it's represent nose level air pollution, mostly depending on how meteorological conditions, it represent the boundary layer concentration of particulate concentration in certain size range. This is a dry mass measured using some either optical measurements or sampler. Whereas the aerosol optical depth is a column value, which represent uh, in other words, amount of aerosol in the entire column of the atmosphere from the surface to the top of the atmosphere. And it's an optical property, so it's not very similar to mass, but it's also represent the particles. Optical depth also is kind of a function of at which wavelength you are making measurement, what kind of particles there are, their shape, size, chemical composition, number, concentration, all those matters. And the another important thing is it's measured in ambient condition. It means it doesn't change. Like in PM2.5, we are trying to actually heat up the sample, air sample, so that we can make measurement at particular relative humidity around 35 to 40%. The aerosol optical depth is in ambient conditions. So if there is a water vapor presence and if there are hygroscopic aerosols, the aerosol optical depth can be different for same mass concentration of particles. So it's there are significant difference between aerosol optical depth and PM2.5, but both of them actually represent concentration of particles in the atmosphere in little bit different ways, and sometimes they can be highly correlated and sometimes they can be completely uncorrelated. So just want to make sure that we get those 2 points. Okay, so moving on, I'll start with the ground networks. And there are many different networks. Again, like models, the ground networks also has nature of local, regional, country level networks to the global networks. And for air quality, the global network, which at least I'm aware of, related to the particle pollution. There are other networks which do the gas measurements. There is Aeronet, which we'll talk more because that's what my current job actually is nowadays, to manage the Aeronet. But then there are other networks like Spartan, which are also co-located with Aeronet, but it provides UPM 2.5 and other chemical composition. In recent last 1 decade, I think low cost sensors have been uh, like you can buy these actually out of the shelf and put it in. They are very cheap. So Purple Air is one of those networks which actually have a very good global coverage. There are almost 30,000 plus monitors currently deployed across the globe. OpenAQ is another source. It's not really a network, but it's more like a data platform which collects the data from these local and government levels, monitors, and provides the data for everyone to use freely. So it's a very good resource. So and then there are other networks like MPLNet, which is a LiDAR network, and individual air quality networks from countries. Okay, so let's talk about Aeronet. Aeronet is a federation of ground-based remote sensing aerosol networks. So it's kind of a networks of networks, and I'll explain why we call it networks of networks. It provides atmospheric measurement from the ground stations. We have long-term, continuous, and readily accessible public domain data sets from this network. When I say long term, we have like 30 years records up to, for certain stations, and then continuously growing. The main data sets which are coming from Aeronets includes aerosol optical, microphysical, and radiative properties. There are some direct measurement and there are some retrieval products. So Aeronet has both direct measurement and retrieve properties. Uh, the data sets have been extensively used in validating satellite data sets, satellite retrievals, climate models, and many air quality applications. Over the years, Aeronet has become like a standard for AOD measurement or aerosol optical depth measurement. It's one of the best ground truth measurement for validating or assessing atmospheric aerosols. So just a little bit on historical side of Aeronet, started in back in 1993. And the idea was at that time to get information on aerosols for atmospheric corrections to derive product like NDVI, land cover. So it was time when AVHR was in orbit and they wanted to get NDVI to characterize the vegetation on the surface. And to do that, you need atmospheric correction. And there was no aerosol data available at the time. So the sun photometer community started making these measurement, and that's how the network got started. Slowly, other countries joined the network. France started their own network called Photons. Canada started their own network called Aerocan. Spain has their own network called RIMA. Australia has their own network called Aerospan. So there are many, many different uh, partners who started joining Aeronet. Uh, and NASA's role was more of a collaborating with all these partners and making sure that we maintain the data quality, maintain the standardization of the instrument. So across, no matter which country operates the network, the instrument is standard, the same instrument is used. We use same calibration facilities and same calibration methodologies across the network. The data processing all happens at NASA. So all the data are consistently processed using same algorithm, and then we distribute data in real time for everyone to use. So it's a very consistent way of uh, supporting the data distribution and providing high quality data. Currently, we have about 538, or it varies between 500 600 station. All time we have 1600 plus deployment, and currently we have footprint in 100 plus countries. So this is the instrument which we use for Aeronet. It's called, manufactured by a company Simel in France. And this is a basically a sun photometer, automated in nature, as you can see. It look at the sun, it look at the sky and makes the measurement in different spectral channel. It has a different version of the instrument with the standard polarized version, and then C prism, which is used for ocean color measurements. So we make all these measurements looking by sun in daytime and sky, and then the moon in the nighttime, and then derive optical, microphysical, and additive properties of atmospheric column aerosols. In addition to these standard ground measurement or the ground permanent sites, Aeronet also participate in field campaigns. So there are field campaigns happens all the time across the globe, whether they are done by NASA or other agencies. It doesn't matter. Aeronet does participate in those field campaign. We have on our website list of all the field campaign which Aeronet has supported over the time. And the two most recent example is just from last year. One is in Asia, where we did deploy instruments in South Korea, Taiwan, Philippines, Thailand, and Malaysia, along with some aircraft measurement. And we had another one, SpaceX, here in California and US, specifically to validate the new NASA mission called PACE. So typically these field campaigns have a different focus, and Aeronet plays a critical role in those measurements. When we deploy the field campaign, typically we deploy high density of Aeronet. So in this particular example, if you see this animation here, in 2011 in DC Baltimore area here in US, we deployed about 45 signals and photometer in very small areas. So every 10-15 kilometer you will have one CML. So the idea is to get a special gradients in aerosols from the ground that we can actually validate those pixel level data from the satellite. So it's a very, very powerful tool from Aeronet. We call them Dragon. They are deployed in large densities. In addition to those two capabilities, Aeronet also provides measurement over ocean using not these commercially available microtops. I'm sure many of you are familiar with the microtops. And the idea here is that whenever there are research vessels on sea or the merchant navy ships, people who are on those ships interested in making measurement, Aeronet provides this microtops on loan basis, and they takes the instrument, they bring it back, we calibrate it with the CML, so the data consistency is very accurate. It is calibrated against the standard CML and photometer. So in that way, over the last 20 years plus, we have collected actually many crews all around the globe. As you can see on the map on the left, we have a good coverage. So if anyone is interested ever going on a cruise, if they need a microtop, please don't hesitate to reach out to me, and we will be more than happy to actually provide a microtop for your measurement. Uh, Aeronet OCs, ocean color monitors, these are another type of instrument which well, they are a version of CMLs and photometer. But as you can see in these pictures, they are deployed in very difficult location in deep over the ocean, sometimes coastal regions, but often they are off the coast. And the purpose of these is to make the ocean color measurement along with aerosol measurement. So these instruments capable of looking sun, moon, sky, and water all together. But they are very difficult to install and maintain these sites. So we only have about 20-25 sites right now, but these are critical in validating ocean color satellite mission like OCM from OCI from India, Oceanside 1 and 2 I think they had, and then PACE, CVIPs, all of them have ocean color monitors. So this is a fundamental validation tool for those instruments. I mentioned about nighttime measurement. All the new version of CML are capable of making measurement by looking moon. So we just released level 1.5 data from more than 400 sites, and we're working to actually do level 2 data, which is coming soon. This is just a kind of list of all the satellite sensors which have heavily used Aeronet data for their validation purpose. So okay, just example of how people are using their own data. Again, this shows a smoke transport case back in 2023 here in Northern America. So we had a lot of fires in Canada and US, and the smoke got transported all the way to Europe. And what you see on the top left is a RGB image combination showing some grayish smoke plume, and then what you see on the bottom is a aerosol index from the ARMS instrument on SUMI NPB satellite. And the red dots, red colors feature shows basically transport of smoke, highly absorbing aerosols. And what you see here, interesting feature is that at different layers in the atmosphere, the smoke is transporting actually from Northern America to over Europe. And at the same time, there are dust storm over Sahara originating and actually transporting across Atlantic towards the US. So very interestingly, in different layer of the atmospheres, because of the distribution of the winds direction differently, uh, two different types of aerosol are transporting in different direction, and you can monitor them from the satellite. But Aeronet can also pick up the signal very easily and provide a little bit more insight about their optical and microphysical properties, which you can see on the right side. We have uh, good density of monitors, Aeronet's station both in Eastern US and over Europe. And you can see, co-locate actually how the smoke is transporting and how the Aeronet is actually responding from day by day. You can see the red dot shows the presence of smoke, and then it's transport over Atlantic Ocean. We don't have that many, but there are few here, and then it reaches to Europe, and then further. So it's a good way in tracking transport pattern like this. Another quick example here is we, like we said, the network is 30-year-old. We have almost 70 plus site which have 20 years plus records. So you can use to look at really long-term climatological changes in our atmospheric aerosols. So just a few examples. This is on the left is over here at Goddard, 30 years trends almost, and you can see almost 60% decrease. And if you match this with US EPS measurement, this match perfectly because of the Clean Air Act in US. On the right, we see trends over Kanpur. Kanpur is one of the oldest site in India for aeronets, which have 25 years of data records, and you can see some increasing trend, not that big of different, but there are definitely a steady increase. Another study which we did use aeronet data to understand actually how the satellite calibrations changes over time. And to look at that, this is one of the study which we use to by looking Moody's aerosol optical depth data. And what you see here is a bias in how much, so not really bias, but how much percentage of AOD actually falls within predefined uncertainty limits. And what you notice specifically here is around 2010, the Terra modis, which is red line, and the blue is the modis aqua, started diverging from each other. The difference between the two started increasing, and that actually indicating of, we knew from the other studies that the Terra in certain spectral channel has calibration issues, and that actually can be seen in AeroNet data when you start comparing these two data sets. So this is another way of using AeroNet data in tracking how the satellites calibration is changing over the time, and how we can actually correct them. So these are just some example. Aeronet has a lot of trainings. We just did a huge training last year. Those YouTube videos are available online. We have a lot of Python scripts. Online visualization tools have been developed over the years. We also have included Aeronet data now in NASA Worldview. If you ever use NASA Worldview for satellite imageries, there's Aeronet layers there now, so you can actually visualize both ground data and satellite data together. And the data formats are typically ASCII format, but the NetCDF format is also available now. I want to talk a little bit, just one experiment which we started recently doing with Aeronet. As I mentioned in the beginning, we're trying to apply Aeronet data more and more towards air quality application. And since AOD and PM2.5 are not the same quantity, they are different quantity, but they are correlated, and there have been a lot of research in the last 2 decades which actually use satellite-based aerosol optical depth to derive PM2.5 from the surface. So now in this new pilot study, what we're trying to do is we are trying to co-locate Aeronet with some of these low-cost sensors. One which we chose is Clarity Node. It provides PM2.5 and few other parameters. So right now we have actually deployed 20 of these sensors next to Aeronet. The map shows the locations where we have these sensors right now currently working. And the idea is that after collecting about a year data with proper calibration of these low-cost sensors with reference grid monitors, can we develop some kind of machine learning algorithm which convert Aeronet measurements into PM2.5 with an estimate? I know it is not exactly a measurement, but an estimate. So if that, we are making some progress towards that, and I'm hoping in coming time we will have a Aeronet based PM2.5 estimation. It's not measurement, it will be an estimation. So it's very similar to what satellite community is providing, but from more accurate aerosol optical depth measurement. So this is a pilot study. It's still ongoing. Hopefully by end of this year, we will have some more results to show on this. Aeronet website has all the details. I don't have to show that. Okay, so I think that was part from the ground measurement. Now I'm going to move on the satellite remote sensing part, where I'm going to show some specific cases where my group has been involved in developing these products. So I just want to apologize that we don't have a lot of example from India here, but some of them examples are global in nature. Some of them are from other parts of the world, and but you can draw parallels. Methodologies which we have developed can be actually applied anywhere in the world, and we have shown you by demonstrating global applications. Okay, so as I was mentioning earlier in the beginning, there are many satellites which are in orbit, and many provides very useful information about atmospheric or aerosols. And by just looking these RGBs or true color images, you can actually learn a lot about atmospheric pollution or events which happens around the world, like either it's a smog or fog over India, or a wildfire, or a dust transport over Arabian Sea from Arabian Peninsula to over India, or haze in US. So you can actually track all kind of pollution by just looking this true color images, and that's very powerful. But we have reached to the point in using satellite data to quantify the amount and the emissions and the amount in the atmosphere and use them with the measurements at the ground and with the model. So primarily, when we talk about the satellite data, again, just to refresh everyone's memory, we have two types of satellite. One is the in LEO, low Earth orbit satellite, and one is the GEO, which is more recent advancement in satellite remote sensing from geostationary orbit. So the advantage of LEO orbits are they have a global coverage. They have limited number of measurement per day. So depending on the satellite and its swath, for example, MODIS covers entire globe in 1 to 2 days. VIIRS have almost daily coverage. MISR, OMI, and other have varying spatial coverage, temporal coverage, depending on. But they have a global coverage. In certain number of days, they provides measurements throughout the globe. So that is the advantage of LEO. But then we also have a geostationary, which are regional provide regional coverage, but they have very high frequency of measurements. So for example, this is animation from the GOES-R, which is goes east now in over looking over western hemispheres, focusing over US. And this particular satellite provides measurements every 10 minutes, over US every 5 minutes. And for certain events, it can do 30-second snapshots also. So it's a very powerful in terms of the frequency of measurement. And now, due to the advancement in both in technology and scientific understanding, and improvement in retrieval algorithm, we are at the point where we can get actually similar accuracies in AODs, which are retrieved from the satellite, comparable to what we were used to get from the polar orbiting like MODIS, VIIRS, and other sensors. So it's very unique time to be in satellite remote sensing field. We are moving from these globals, less frequent measurements, to these high frequent measurement, but focused on regional data. So here are just some sensors I want to point out from the geostationary constellation. I'm sure many of you are familiar with this. We have two satellites right now over Western Hemisphere called GOES West, which looks most of the Pacific Ocean, Western Pacific Oceans, and US. And then we have GOES East, which looks most of the Western Hemisphere, including North and South America, all the way to coast of Africa. ESA has recently launched Meteosat third generation satellite, which is actually looking over Africa and Europe. It does have some coverage over India at the very end of the swath. And then we have multiple satellites from Asia. There is AMI from South Korea. There is Himawari, two Himawaris, actually Himawari 8 and 9 from Japan, which does cover most of the Asia. And both of these satellites does cover India, up to half of the India. Unfortunately, we don't have anything right now of this capabilities over India, which actually look directly and cover Indian Ocean and Indian region. So these are all very similar in terms of capabilities like MODIS and VIIRS, So these are operates most of them in optical channels and provide capable of retrieving aerosol optical depth. All of them have aerosol optical depth product. Now there is a new generation of satellite which are more focused on trace gases called we have a constellation of these satellites. There are three right now. Well, two in orbit. One is about to launch in summer of this year. So Tempo looks over US. It was launched in 2023. GEMS looks over Asia. It does have coverage over India. Its South Korean satellites make measurement every 1 hour, both Tempo and GEMS. And then Sentinel-4, which will be launched this summer, will look over Europe. So these three satellites together cover most of the northern uh, part of the globe and actually provides hourly measurement on trace gases like NO2, SO2, methane, and most of these measurements are in UV-vis channels. So combining measurements from these two types of sensors is very, very critical in moving forward with satellite remote sensing. So just want to give you a quick example where we actually use these satellites and generated a data sets which has been implemented by US EPA into their system. So a few years ago, we started as Neeraj mentioned, health NASA's Health and Air Quality Applied Science team, HECAST, and under that, we partnered with NOAA and US EPA and took the data from GOES East and GOES West, derived PM2.5, which is a NOAA product, and then we applied a machine learning algorithm to do bias correction using ground measurement. And this data sets actually has been developed and now available in EPA system. So this is first time EPA has adopted a satellite-based product into their system. It's not for regulatory purpose, but at least for providing alerts. So right now it's kind of under review within by the state agencies within EPA, and once it is approved, it will be available in AirNow system. We have a couple of papers which provides much more details on that. This is just showing some kind of results from that particular work, how machine learning actually used to improve the accuracy. So on the left, you have correlation, RMSE, and mean bias from the existing GOES RPM 2.4 product, which is produced by NOAA. And then we took that product, applied machine learning technique, and we improved on all of those statistical parameter. And this improved product is what EPA is using. So it's a great example. We started with the research and then we developed the product and now it is operational and all the methodological details are uh, discussed in this recently published paper in one of the AGU journal. Okay, so let me bring to the tempo. Now we are moving from visible sensors to UV with sensors, which are capable. So the tempo was launched back in 2023. This is first light image, and the map shows the NO2 concentration. And this is first time from the satellite we are looking how NO2 are changing from 1 hour to next hour. And this was never seen before because you're limited with the ground measurement or the measurements from tropomi or OMI, which only provides once in a day measurement. So this first time we have this kind of capabilities. So we started using integrating these two sensors, Tempo and GOES-R, because they have a similar footprint on the ground, similar regions to cover. So we combine these data sets along with the metrology into more complicated deep learning, deep neural networks or DNN to see if this, in addition to GOES-R, does Tempo add value or improve the accuracies in PM2.5. And one of the things which we noticed that it does, because when we were using only GOES-R, we had difficulty in retrieving high PM2.5 concentration, specifically during the wildfires. So as you know, US has a lot of wildfire in more recent time, and whenever there's wildfire, the PM2.5 can go very high. And GOES-R alone, because it doesn't have the absorbing type of aerosols capability, didn't have that. We didn't have those accurate estimations. So by including tempo, we started actually seeing those improvement. And I'll show you just one example here. So what you see here is a uh, measurement on different uh, time for particular stations. The red shows, the orange red shows estimation from the GOSAR alone, and the blue is the ground measurements. So you can see significant underestimations from the GOSAR, but when we included the tempo, because tempo has UV channels which are specifically sensitive to absorbing aerosols, and they are also sensitive to the height of the aerosols in the atmosphere. So by including tempo data into the machine learning algorithm, we see significant improvements. So this is just one case. This paper is under review right now, and this product should be coming soon. Once the paper is accepted by this summer, we will be able to uh, process this product as an operational product. So moving on to the global region, from that learning, we have these many sensors which I described earlier from geostationary and the legacy LEO orbits like MODIS and VIIRS. So we started combining these because it becomes very challenging for the users to use the data if they are not, because there are so many sensors, so many different formats, different spatial temporal resolutions. So it becomes nightmare for users how to exactly use the information in most consistent way. So we have an efforts where we actually took all these data sets, applied same retrieval algorithm, modis.target, and then combined them into an equal angle data grid. And that's where we actually, this particular project is. This data is already available. We have all the technical details in our recent last year's paper in AMT, and it basically provides 30 minutes global data sets at quarter degree resolution, which is otherwise not available. So you have a global coverage. Now you will notice that over Africa and Europe, we don't have that big of coverage because we don't have geostationary satellite available yet. I mean, there is a recently launched FCI Meteosat third generation, but that has not been yet incorporated in our data analysis. Okay, so I think that is all on the satellite. Now let me just quickly take maybe 5-7 minutes on modeling efforts, which we have been doing, which also include machine learning and AI methods. Okay, so the modeling for, we rely completely on our Global Modeling and Assimilation Office, GMAO, here at NASA Goddard. Its core mission is to enhance the values of NASA's observation, to understand, analyze, and predict changes in physics, chemistry, and biology of Earth system. So it's a very Earth system model. It's a global model. It runs at 25 kilometers globally and have provided many different products. So here are the different data products or different ways in this GEOS system is used. We have a near real-time weather and chemical forecast. We have a reanalysis, MERA2, for example, which many of you probably have heard or used it. In addition, there are some other products like seasonal to sub-seasonal decadal predictions, very high resolution runs for specific events like hurricane or a smoke or wildfire transport. And then it is also heavily used for assimilating or simulating the observing system. So whenever there is a new satellite, the data, the GEOS is used to simulate those measurements ahead of time to understand the data format, the data capabilities and everything. So it's a very robust system. Um, the two data sets which we have used in our study, and I'm going to talk quickly about, one is MERA2. I'm sure many of you are familiar. This is a used GEOS assimilated system. It means it uses a lot of satellite data and ground data to be assimilated in the model, and then the output is created at consistent half degree grid. And this data is available for last 40 years from 1980 to current time. Um, it does have meteorology, aerosols, ozone, and many other parameters. So this has been heavily used in our research and other people's. The other one is GEOS FP. This is a forward processing model, which provides forecast of atmospheric aerosols, meteorology, and other parameters. It is run at 25-kilometer grid, and it provides 10 days forecast. So 5 days and 10 days forecast, depending on which field you are looking. And it is, I think, initiated twice a day. So twice a day you get next 10 days forecast. So we use these two outputs, MERA2 and GEOS FP, in some of our studies. So this is one example. Back in 2021, we published this study actually where we took the MERA2 and GEOS, metrology and aerosols, combined with the surface measurement, and then came up with this historical and forecasted PM2.5 over Thailand. This was part of a NASA surveyor and Thai Pollution Control Department joint study. And as you can see, when we compare the MERA2 directly without any corrections with the ground measurement, you will see a performance like that, which is not bad, but you see a lot of spread here. When we actually used the machine learning, did some bias correction, we were able to get it very accurately. And this still, you will see there are some underestimation at the higher end. And I'll show you this is a typical problem in machine learning and related to the data distribution. So we do still have some issues, but it still shows pretty good relationship. So this method has been adopted, and then we implemented in the forecasting framework and actually developed a tool which is now operation by Thai Pollution Control Department in Thailand. And this provides 3 days air quality forecast every 3 hours with real-time validation capability. So this is a good example where we have actually took some of our research and made it operational, which has been used by these environmental monitoring agencies. This is another example which is very following the similar method, but we did the same kind of analysis over US. And again, we published this in one of the AGU journal. You can see in this example on the left, the green line shows the raw MERA2 data. And then when we bias corrected with the machine learning, we are able to actually correlate it very well with the ground measurement. Now, remember, we do use ground measurement to calibrate the machine learning model. So but we use tenfold cross validation type technique to ensure that we are not comparing the same data sets which are being used to train the model. So there are some caveats in when we use the machine learning, and this paper discuss much more technical details on this particular aspect. So after actually doing this analysis over US and Thailand, we got good confidence that probably we can expand this to the global region. So we went to the global. Now, the problem with the doing globally that the data density is not as good as we had in US and in Thailand. Now, as you can see from this map, this is the data which we got from OpenAQ platform, which shares the data. And we had some data, but like entire Africa is almost empty, Middle East is almost empty, South America is almost empty. So there is a huge challenge in actually doing machine learning modeling over regions where we don't have any kind of data sets from the ground to calibrate the model. So we use various different ways in which we have done and developed this product. So this is the results from the global analysis. So we started with this, which is on the top right. You see, this is a original MERA2 without any calibration or any bias corrections. Correlation is around 0.4. When we started applying various ways in machine learning, we were able to get to this level. Now, correlation has increased significantly, but there are still problems, which you can see on the right side. You have observed on the x-axis, and then the y-axis, we have biases. On the bias, you will see that around up to 200 microgram per cubic meter, we are pretty good. We are very close to zero. But as the concentration start increasing, goes very under very polluted regions, we started underestimating. And this again is same problem as we saw earlier over Thailand, is the data distribution. We do not have enough measurement in our training data sets which can represent the higher values. So the model is very fine tuned towards the lower concentration, because if you draw the histogram or the frequency distribution, the distribution is skewed towards the lower concentration in most of the world, or at least where we have the measurements. So this, to overcome this problem, we started using some more techniques, data augmentation and other techniques, which are coming up. So this work is right now in preparation, and hopefully we'll be able to submit it soon. These datasets are actually generated and available in NASA DAC, and also in the Giovanni for people to use. So this is exactly bias corrected PM2.5 from MERA to at global regions. So it's available for everyone to use. Another quick example from the modeling, we have a project with the Department of State. As many of you know, State Department have these ground monitors at many embassy locations. If you have following the news, you might have noticed that last few weeks these monitors stopped working because of the decision taken by the Department of States. But we have partnered with them for a long time, and we developed this a forecasting tool very similar to what we did for Thailand, but these are specifically over US embassy location. We use GEOS FP, aerosol and meteorology. We use DOS air measurement to calibrate the machine learning model, and then we provide this localized 3 hourly forecast for next 72 hours or 3 days. So this project was again very successful. We implemented actually this into Department of State's decision making system, and it is an operational product right now. So we did a thorough global analysis on this. This is just showing an example of how the forecasting actually compares with the ground measurements. So the black line is the ground measurements, and those colored lines are the forecast originated in different days. So you can see it's not one-to-one comparison, one-to-one agreement, but forecast does captures broadly the air quality pretty good. We have done global analysis on this evaluation. The paper is under review, should come up. But this particular project was actually implemented in Department of State's. Unfortunately, this Zapier has been discontinued last few weeks, but now the data is available in our own system for anyone to visualize or download. We have shared this data for India also with IITM Research Group, who have compared a 13 different models over Delhi region. So this has been used over India as well. Okay, I think that's all I have. I hope I have not gone over time, but I'll be happy to take questions now.
Okay. Thank you so much, Pawan, for such an interesting and very informative talk. I'm sure there will be many questions. So now I request my colleague, Dr. Shani Tiwari, to take care of question answer session. Shani?
Yes, sir. Yes, sir. So the platform is open for question answer. So anyone who has any questions, they can ask. And if there is any problem in mic or communication, they can type on invite chatting session. We will read from here.
Okay, Pawan, until other people raise their hand, let me take the opportunity and ask. Okay.
Sure.
So I just curious to know, means I know there are satellite measurements are keep on improving in terms of temporal scale and spatial scale. It was already there. Are there any plans to increase the composition of aerosol? Say, means at least say which are biologically important, for example, black carbon or sulfate or direct measurement through satellite. So are there some efforts?
Yeah, so Neeraj, that's a very good question, and I think that's where satellite community is moving now. So as you see these UV measurements, which we have recently from satellite like Tempo, GEM, Sentinel-4, TROP, OMI. They have capability to do the gases part like NO2, SO2, methane, formaldehyde, ozone, right? But the particle part is not yet there. There's a new mission called Maya. Uh, it will be launched hopefully either end of this year or early next year, and it is very focused on health studies. And one of the primary goal of that is to get the chemical composition of atmospheric aerosols or PM2.5. It will be a targeted missions only over some of the 20 different big cities around the world. Delhi is one included in that, and it will provide PM2.5 mass concentration along with some composition of I think sulfate and nitrate and maybe carbonous aerosol. So there is a plan of data product on that. Those algorithms are, it has a, in addition to simple spectral measurement, it has an angular measurement as well as polarization. So it does have three different ways looking the same target, and we are hoping that combining the kind of information will enable us to provide chemical composition.
So if I can add one more question here. Means I know means you are not from the technical development of instrument background. But what are the limitations? Why people can measure gases but not aerosol? What are the technical limitation in there?
Yeah. So I think in order to do the chemical composition right for aerosols, uh, we have to have spectral measurements and enough signal, because again the limitation is that you are looking from 600-700 up in that up in the sky and trying to pinpoint the chemical composition. So you need to have very strong signal coming from that particular things, right? So let's say we want to distinguish sulfate aerosols, and if it is not dominating in rural areas, in urban areas may be possible, but it's rural areas the signal is very small. And if you do not have a specific spectral channel which can actually separate that signal from the rest of the background, because there are many aerosols, there's
Yeah.
cloud, there are gases, so it's become a little bit scientifically challenging situation. But since now we have advancement in technologies in data storage problem, earlier we used to have like a lot of data storage problem on board satellite. Now we are able to actually do very hyperspectral measurement in very narrow spectral band, looking polarization. So I think we are moving towards that direction, but we are not there yet.
Okay. Thank you. Over to you,
So,
Shani.
yes, we have a few questions from our audience. So, one is from Jintu Bora. So, he is asking about that whether ground measurements using gas sensors are effective in air pollution monitoring.
Sir, can you please say it again? I'm sorry,
Yeah.
I couldn't.
So, he is asking whether ground measurements using gas sensors are effective in air pollution monitoring.
So yes, means traditionally ground measurements are used for actually gases measurement like NO2, SO2, ammonia, CO, and other measurements. So traditionally ground measurements have been used. If you're talking about just the low cost sensors, then yes, there are a lot of problems there. But the high quality standard reference grade monitors have been used and they are very accurate.
Oh, thank you. In next question from Yas Daima. So he is asking in the study of estimation of PM 2.5, what parameters other than the aeronet observations and meteorological data are you planning to include into the machine learning models?
Yes, so we do plan to use metrology. For example, temperature, relative humidity. As I mentioned, relative humidity is very important to make sure that we are actually accounting for the hygroscopy in aerosol optical depth. So relative humidity, temperature, surface pressures tells us about the topography and the overall and then the winds. wind direction and wind speed. These are kind of typical meteorological parameter. We like to use boundary layer height, but typically the accuracies of boundary layer height which we get from the models are not very accurate. So we don't have that kind of measurement, but that is one of the most important parameter in calculating PM 2.5 from AOD measurement.
Okay, so exact estimation of PBL can also enhance the data accuracy in estimations.
Yes, yes,
Okay,
but
so
unfortunately, there's not too many measurements of that.
okay, one additional in addition to these questions, what is the threshold value? Can you give the numbers, the threshold value to consider the RH value, threshold RH value for the considerations of PM 2.5 in estimation?
I'm not sure if I understand the question, but let me tell you two things. One is when we make measurement of PM 2.5 using standard instruments like BAM, or then we heat the samples and bring it to about 35 to 40% relative humidity to make sure that it is dry mass. So that is the standard practice in air quality measurement. Now, if you're talking about the threshold for when the hygroscopy start making effect on aerosol properties in optical,
Yes,
then that is, so it is very high actually. It's about 80 to 90% depending on aerosol type. So if you take sulfate aerosols in urban environment and
yes.
start looking their extinction efficiency, then you will see that it is significant exponentially increase when the relative humidity goes from 80 to 85% or 90%. So after I would say 80%, 82%, it exponentially start increasing.
Okay, thank you. Another question
Yeah.
from the Mr. Narendra Reddy. Are these machine learning models which are used for the Mira 2 bias to the public?
They are not, but if anybody is interested, we can make them public. It's we have a GitHub repositories and we can make them available.
Okay. So one question from Brajesh Singh from IIT Roper. So we have almost a 500 plus CPCB hourly daily data set. Can we use or compare or validate it with the satellite data sets? I think it is yes, we can. Can I estimate the concentration of PM 2.5 or 10 of places where ground measurement is not available by what analysis and techniques? By what analysis techniques?
Yes, yes. So the short answer is yes, you can do that.
Yes.
Um, so when we did our global analysis, we did not have access to those 500 measurement. But if you have access and if you want to do that analysis, I will be happy to help. We'll be happy to provide the satellite data on those locations or meteorology from Mara 2 or other. So there are, I would say, thousands of papers actually published on that particular topic in the last 2 decades, and people have described the methods. There are simple statistical ways, machine learning ways, more geophysical modeling. So there are a range of methods in which you can actually do. And once you have those models developed and generalized enough, you can actually estimate in location where you don't have ground measurement.
Okay, we have questions from Meher Rajpradhan. He is a high school student and he just asked questions. What are the problems that satellite generally face after CubeSat is just deployed in space?
Okay, so I'm not too much
Yeah,
sure about the CubeSat satellite because they are very small satellites, typically not. So I can give you one example, right? So you may have heard the GeoEye or planets type of small satellites or CubeSats. They are typically used for land mapping. They don't have these kind of spectral channels to get some of these atmospheric properties. Often they are used for high resolution land mapping, or so I don't know what kind of problem they have. They are typically deployed in low Earth orbit, like 200-300 kilometers. So their lifetime in the orbit is not
up to the mark.
long. Maybe,
Yes.
yeah, maybe year to year most. I think not that long.
Okay, another question from Mohammad Zaid. So how can we downscale the satellites based model PM 2.5 model data?
Yeah, so I think the downscaling is again a new emerging field. Um, the problem with the downscaling is that you are relying on statistical techniques to downscale. Let's say Mera 2 is at half degree and you want 5 kilometer data product from Mera 2. Yes, you can do it. There are machine learning ways to do it. There are statistical ways to do it. Uh, but the problem is, unless we have some kind of a training data or a validation data to validate those spatial scales, uh, it is anyone's guess. So downscaling is kind of a new field that rely a lot on mathematical and machine learning capabilities, but validating those spatial pattern is very challenging. I mean, satellite data can help you up to some
Yes.
extent, but it's still a challenging problem.
So another question from Ria Mahendra. So what is the difference between Mira 2 machine learning that you mentioned and Mira 2 CNN? Because Mira 2 CNN is also derived from the machine learning.
Yeah, it's the same thing. Uh, so there's no difference between Mera 2 ML and Mera 2 CNN, probably used interchangeably. CNN is, like you said, is one of the type, a convolution neural network type
Yes.
of machine learning algorithm.
Okay. So one question from the YouTube channel, our YouTube channel. How do you calibrate those measurement system on satellite?
Okay, I'm not sure if I understand the question. How do I calibrate satellites itself?
Those measurement system on satellite. I think this
I
question
think they
is
are
little
talking
bit
about sensor
sensors.
concept, right? Validation of
Yeah,
this calibration of sensors.
so yeah, so satellite sensors do have onboard calibrations. For example, so when satellite is launched in the space, right? First they calibrated in the lab on the ground. Okay, so they are pre-deployment calibrated, and once they are in orbit, there are different ways in which we can calibrate. One is by looking. So if they are optical sensors like MODIS has a capability to look at the moon on time to time and then calibrate itself. So by looking moon, basically you're looking a constant source of light at certain time only in certain phase of the moon. And if you do that at regular interval, then you can see how your signal is changing over time or not. Because your source is constant, so you should not see any difference in your signal over the time. If you're seeing this difference in this signal, it means there's something happening to the instrument, the calibration is degrading, and then you can correct for it. So that is one way. There are other, depending on which channel, there are some ground uh, targets like Saharan deserts or New Mexico sand or deep oceans, where you can actually look. Those surfaces are relatively constant in time, so you can look those surface over time and time and see if signal is changing in the satellite. So those are different ways in which you can actually calibrate the satellite in the orbit itself. And most of the satellite do have those kind of capabilities inbuilt.
Okay, the next question is from Dr. Ira Upadhyay. She has two questions probably. One is from how do you how do uncertainty in model outputs and parameters impact forecast accuracy? And the other one is what challenges arises in using satellite data for air quality monitoring in regions with high cloud cover or aerosol load.
Yeah, so yes, I think if you have high uncertain errors data input to the model, definitely it will actually affect the accuracies of the output, right? Whether it's forecasting or estimation, doesn't matter. Now, if we know what kind of uncertainty ahead of time, then models have ways in which you can actually propagate the uncertainty along with it, and then in forecasting you will see that okay, this particular forecast has this kind of uncertainty associated with the input. But often, more than often, we don't know actually what kind of uncertainties are there in those input parameters. For example, let's take an example of low cost sensors for PM2.5 measurement. We know for sure they are uncertain. Often they overestimate, they underestimate during the wildfires, they underestimate during the dust storms. But quantifying them is very difficult because each sensor is different. The sensor to sensor variability is such a large, quantifying them it will be very different. And if we don't have a consistent bias, then it becomes noise problem, the data noise problem, because there's so much variability that we are not able to actually say that okay, these particular sensor will overestimate by 20% or 25%. We
Yes.
cannot say, because that 20% can be 100%, it can be
Yes.
1%. So that is one problem I think I see in making uncertainty available either for input parameter or output parameter. Now, going to the second question, in the cloud regions or high aerosol. So we don't see any problem in high aerosol loading regions. Like there's typically no problem from the satellite unless it is very, very thick smoke plumes, which satellite can underestimate, sometimes can see, assume as a cloud. In cloudy conditions, so far, unless we use some of the lidar measurement like Calypso, we don't have capability actually to look aerosols under cloudy conditions. So if there is a cloud, we will detect it and mask that data. It will not be useful for air quality monitoring or for aerosol retrievals. So in cloudy condition, we can't do anything. We do have some techniques to quantify AODs on top of the cloud. If there is a layers above the cloud layer, then we can actually quantify that. Below the cloud, its visual sensor cannot penetrate that unless it is an active sensor like lidar.
Okay. So another question from Vaibhav Bangar. So he's asking size segregation of AOD in fine and coarse mode using satellite remote sensing is effective?
So it depends on which satellite sensor you are using and which algorithm you are using, as there are many different algorithms. So Modis has a fine mode, coarse mode, which people has validated historically, both over land and ocean. And as far as I remember, it 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 has significantly higher accuracy over ocean compared to over land from the Modis. Miser also has, which is little bit better product, fine mode and coarse mode, and then it is actually little bit higher accurate accuracy over land also. Other than that, there are like Pace, I don't know, they might have a new product because Pace also has sensors which are very hyper spectral resolution, like 5 nanometer type of sensors. It's
Mm.
still very relatively new sensor, so we don't know all the data product which will eventually come out of that sensor, but that also has capability to get better estimation for fine and coarse mode.
Thank you. One last questions from RK Sarangi. So he is asking Indian satellite inset data based on AOD product at 550 nanometers. Can it be assimilated with the other satellite data to have merged global products?
Yes, so uh, yes, I think there is a product, AOD product from Inset.
Yes.
Uh, the problem with the Inset is it's a broader channel. It's not very narrow band channel like Modis or Wears. It's a broader channel, I think, um, covering the entire visible spectra from 5 400 to 700, I believe. I don't remember exactly. So it's a broader channel. The spatial resolution is also a little bit, but if there is a product and if it is validated, um, you can definitely combine with other satellite products to enhance the global coverage. I don't see any problem. I don't know any efforts in that direction from anyone yet, but if anybody is interesting, we will be happy to help. We have done that for others, many other satellites.
Okay, thank you. So all questions from chat box is over now. So anyone still have any questions, they can put some question. Otherwise, they can raise the hand and ask the question directly. Okay, one more question from the Divya. Aeronet is also giving the radiative forcing, which is more reliable radiative forcing derived from SB dot or Aeronet.
Yeah, so Aeronet, so when you look at the Aeronet inversion product, which are retrieved using a retrieval algorithm, which include single scattering albedo, size distributions, phase function, refractive index, and it does have radiative forcing, depolarization, few other parameters. So Aeronet has certain parameter which we recommend to use. Radiative forcing is, it's, I would say it's one of the byproduct. It is not primarily designed, it's just top of the atmosphere radiative forcing which comes as a byproduct from the retrieval algorithm. I am not aware of if anybody has validated it or not. I don't think anybody has validated that product, so I don't know how good that product is compared to other estimations based on other ready to transfer codes like SP dot or anything else. So I'm not sure whether it's good or not. Typically, we don't use that. It's more of a diagnosis parameter for us.
Okay, one interesting question from Kamran and Sari. When different satellites retrieve AOD are merged, does the overall AOD uncertainty decreases?
No, actually. So
Yes.
depending on how you merge, right? So for example, in our 6 satellite sensors, we use the same algorithm. If you are using a different algorithm, then uncertainty can be challenging to quantify because each algorithm has a different way of accounting the uncertainty. But in our case, we did same algorithm is applied, same spectral channels are used, and then we also retrieved everything on the same spatial resolution. Uh, and that allows us to actually consistent retrieval output and merge them together with the same quality assurance. And when we compared the actually in the paper, you will see that when we compared with ground measurements and Aeronet, we saw results very comparable to individual sensors uncertainties. The differences, the biases, nature of biases, characterization is very similar if you look individual sensors. So I don't think it definitely decreased, but it is it. I would say it's more closer to the original census.
Okay. So now all questions are over. If anyone have any questions, so please raise your hand. I think all questions are over. So now I am going to, yes,
Yeah,
sir.
no, yeah, continue to the last part of the talk.
Yes. So now I'm going to give the vote of thanks. So first of all, on behalf of entire IASTA family, I would like to thank everyone who joined here for this today's insightful lectures. And a special thanks goes to our distinguished speaker, Dr. Pawan Gupta, for sharing their valuable expertise and knowledge with us. The talk on air quality monitoring and forecasting using synergistic approach from satellite to the ground-based measurements and our model data sets. Not only very informative, but also quite interesting. So the way he explained the remote sensing application in air quality with such a clarity, it sparks the curiosity and the enthusiasms and inspired all of us. The question answer session, particularly the question answer session, is really enriched the discussion that made the today's lectures more meaningful. In addition to this, a heartful thanks to our organizing committee for their hard work and dedications to make these events successful, and we are continuously having every month this type of lectures. In the last, our sincere appreciations goes to our sponsors and supporters. Once again, very thank you, Dr. Pawan Gupta, for your enlightenment talk, and thank you everyone for presenting here to make these lectures a memorable one. Thank you all.
Thank you.
Thank you. Thank you,
Thank
Pawan,
you.
for considering our
Thank you,
request
Pawan.
and getting so early in the
Yeah,
morning.
no,
Yeah.
not a
Thank you,
problem. Thank
Sunny.
you, everyone.
Thank you.
Thank you.
Thank
I
you.
Thank you,
really
sir.
enjoyed
Thank
it.
you.
Thank you. Thank
Thanks.
you.
Bye bye.